So, what we're going to talk about today is the ladder problem. Right, a ladder problem is kind of a variation on a beam problem, but it's a ladder up against a wall, so nothing too weird or strange there. So, there we go. And we could also have someone on our ladder, like a painter. I don't know why it's always a painter in this book. Actually, in the book, it's a painter or a monkey. Yes, monkey on a ladder. Guess what your homework is? It's the monkey on a ladder problem, problem 41. But anyway, so I've got a ladder resting up against a wall. We're not going to put any additional load on it, but let's talk about the forces that are in place. So unlike the boom or the beam, where there's like a fixed hinge down here, that doesn't exist. So let's talk about the forces that are acting down here. Well, clearly, I've got a normal force from the floor, right? But if you think about it, I've also got a normal force here from the wall. So I need to differentiate those. Normal force floor, normal force wall. What else do I have? Well, I'm going to have the weight of the ladder acting there at its center of mass. Now, let's talk about that, because if I have a ladder up against the wall, like if you have a meter stick or a broom or anything up against the wall, you might have seen that if you don't angle it right, what'll happen here is that this lower edge will slip in this direction, and then this edge slips down the wall there, and the ladder falls. We don't want our ladder to fall. So there's got to be something to prevent this point of contact from sliding to the left. Now, something that painters actually do to protect themselves is they'll attach a rope here and attach it to the wall to provide that. But for us normal schmucks, what we're usually using is static friction, right? And so there it is. There's a static frictional force with the floor there. But if you think about it, if that's true as well, that point is being held from translating to the left because of contact, there's also a static frictional force here on the wall. Now, in the first problem that you're going to do tonight, they're going to tell you that the wall's frictionless. That's going to make this problem easier. Not in the second problem, which is why it's a more difficult problem. But here we go. We're still only going to be looking at this problem while the ladder is in static equilibrium, which means that we can pick a hinge and know that that hinge isn't going to change. So I'm going to pick there. So what does this look like then? Well, if I say our normal up to the right and counterclockwise are positive, we can see what's going on with this. So if we look, sum of forces in the x direction is equal to max, right? All we have here is static friction from the floor, right? Minus Fn from the wall is equal to 0. Sum of forces y is equal to may. Well, with friction, this would look like Fsw plus Fnf minus Fg is equal to 0. And then we'll talk about sum of torques in a second. But I didn't want to point something out. Notice that these are static frictions, not maximum values of static frictions. In order to have max values of static frictions, I would have to have limit statements, which is going to be something that's going to happen in this problem. But it's important for you to recognize that this maximum static friction, so if I talk about FSF max, would be based on this normal force at that point of contact in the same way that FSW is going to equal, or max, mu sub s times Fnw. And these two mu's might not even be the same if these surfaces are of different texture. So there's a lot of complication and variation that can go into this problem. Right, so let's just, I'll just leave that for the moment, and also then talk about sum of torques. So sum of torques is equal to I alpha, and that's going to go to 0, 0, 0, right? So what's going to provide a torque? Well, looks like the positive torque due to NW, a positive torque due to SW, and then a negative torque due to G is equal to 0. So let's just look at what those would look like. So that's F and W. And so what would be the lever arm distance? Yep, it would be this here, which means that all of this is based on the angle of inclination of the ruler. And so that's going to be the vertical part of this. So sine of theta plus FSW, and then L, whole length, sine theta. L, in this case, it would be the cosine of theta minus FG, and then this is L over 2. And then it's just this part. So cosine of theta is equal to 0. And then it's just depending on what's going on. If I had, like, say, for example, I don't know, a monkey here, that would add a force here, and it would add a torque there. And then you can see how the problem could go in terms of variations of, there's no friction here. That simplifies these equations greatly, and you can see how that goes. So you're going to play with the ladder problems. The only thing that's different from the ladder than the boom is rather than having those pivot forces, I have frictions and normal forces. So that's not really all that different.